Hello guys, it is nice to see you again, virtually at least. I would like to welcome you to my 486 part selection video. I have decided my episode 4 to be about the 486 generation with Vesa Local Bus in particular. I have always liked Vesa Local Bus. I have no idea why. It was short-lived because Intel pushed on PCI and it had many problems and flaws, compatibility and instability issues among others. Despite that, my love for Vesa Local Bus stays strong to this day. It was the first proper local bus and it impacted mostly video performance in both games and graphical user interface, of course when it worked properly. I will now show you all the parts I am going to use in my 486 build video. And having said that, guys, if you like this video, please give me a thumbs up. If you don't like it, dislike it. And if you like my channel in general, please subscribe. You will help me that way to achieve 100 subscribers, and that will allow me to change my channel's name. Now I'm gonna reposition my camera in order for you to see better, so see you in a while. I will start, of course, with the motherboard. It is a UMC chipset motherboard. UMC stands for United Microelectronics Corporation, and those guys are still going today. I did not find much information about it, but from what I see, it's a midlife 486 motherboard. Earlier 486 boards only have 8 and 16-bit ISA, and later ones have PCI, so this is a typical midlife 1994 motherboard. I have some worries about it. It should have 256 kilobytes of level 2 cache. I say level 2 because my level 1 is in my glorious Cyrix CPU, 8 kilobytes of it. That level 2 cache, however, is directly soldered to the board, and this is a pattern found in fake cache motherboards that flooded the market in the mid-90s. Back to this motherboard layout, as you can clearly see, fewer chips on less space than the 386 motherboard I presented you in episodes 1 to 3, because as computers evolve, less chips do more stuff, with culmination in this system on a chip concept. This is the main chip of this two-chip chipset, both designed and manufactured by United Microelectronics Corporation. Inside this baby here, the memory controller with support for fast page memory, a type of memory that is a bit slower than EDO because of the way it handles the column access trope. Cache controller is inside as well, with support for, I presume, up to 1 megabyte in size, and TAC addresses. That's why we have this 9th chip here. All of them are for cache, but this is for TAC addresses. And that said, CPU interface is inside. Power management should also be here, and of course the bus mastering for the Vesa Local Bus slots as well. This one, the real-time clock is here. You can see the time crystal and a hex inverter right next to it. It's also connected to the system's BIOS. Of course, the DMA controller is inside. It manages interrupt requests, and the CMOS to store system settings. What else? A couple of octo buffers and line drivers with 3-state output, and some octo bus transceivers with a 3-state output for the ISA slots. What else? Inline resistors, normal resistors, and some electrolytic capacitors. Something interesting I have noticed here on this chip: a couple of pins are bridged together. I don't have the datasheet and I don't know why they did that, but if you know, please leave a comment. I will use two 8 megabyte fast page mode modules for a total of 16 megabytes of system memory. That's twice as much memory as in my 386. Here, as you can see, the star of the show, that's our main system processor, the Cyrix Cx486DX2, working on blazing 80 MHz, and that's because it has a clock multiplier inside. It doubles the system bus. In this configuration, the system bus is 40 MHz. It also has 8 kilobytes of level 1 cache inside, I told you that, and it operates on 5 volts. This green heatsink is permanently attached by the manufacturer. This baby here was introduced in November 1994 and had similar functionality to the Intel 486DX2, from which it was partly reverse engineered. Intel, of course, filed a lawsuit, but the fact that Cyrix had made their own compatible design based on the reverse engineering led to Intel losing the case and paying $12 million to Cyrix to drop an antitrust case against Intel they filed in reply. What can I tell you, heavy corporate shit? There is also a low power version as well that works on both 3.45 volts and 5 volts. Actually, I'm not sure if mine isn't that one. And we have come to my beloved Vesa Local Bus slots. And speaking about local buses, it is time for a quick cave sheet presentation. And I'm still using CaveSheet Pro version BC 1990, but as you can see, it comes with a new wallpaper. I will now explain you the original concept and the local bus concept, but before that I need to make an important remark. This SS here, it means slow speed, not Schutzstaffel. I take World War II very seriously. What is important to know about the original concept here? In the beginning, the ISA bus was a form of a local bus as well, because it operated with the same speed as the CPU, but with CPUs getting faster, they needed to separate it and attach it to the main chipset in order to preserve system stability. So slow speed buses appeared as well as high speed buses. This applies also for ASA and microchannel as well. You can see them here. Cars just could not cope with faster speeds, so those buses eventually became much slower than the system bus and the CPU, which led to a bottleneck effect. You can see on the high-speed bus the CPU, the main chipset, the external cache and the system memory, and on the slow buses it's the internal input-output and the slots input-output. It could be ISA, ASA or microchannel. And on the right side of our beautiful cave sheet, the local bus concept. This concept connected the newly created Vesa Local Bus and later PCI and AGP to the high-speed system bus again. That was great for video cards and input-output controllers, but as you will see later, it was a problem for Vesa Local Bus operation because it was not designed properly. The old buses were left where they were to preserve backward compatibility. The major reason for the development of the Vesa Local Bus was to improve video performance in personal computers. The Vesa Local Bus was the most popular local bus design from its debut in August 1992 up to 1994. It was created by the Vesa Committee, a non-profit organization founded by NAC to further develop video display and bus standards. The Vesa Local Bus can move data 32 bits at a time. Actually, this part of the connector is connected directly to the CPU. This enables data to flow between the CPU and a compatible video subsystem or hard drive at the full 32-bit data width of the 486 chip. The maximum rated throughput of the Vesa Local Bus is 128 to 132 megabytes per second, and this is a huge improvement from the 8 megabytes per second that ISA can handle. Vesa Local Bus also provided a substantial boost in hard drive performance. because 16-bit ED drive and interfaces can achieve a throughput of 5 megabytes per second, whereas Vesa Local Bus hard drive adapters could achieve a throughput of as much as 8 megabytes per second. Unfortunately, it is time to address the elephant in the room, the drawbacks that led to Vesa Local Bus's fast demise in favor of PCI. By a mile, the most evil ones are: first, a major problem, dependence on a 486 CPU. The Vesa Local Bus inherently is tied to the 486 processor bus. This bus is quite different from that used by Pentium and later processors. A Vesa Local Bus that operates at the full bus speed of a Pentium system bus has not been developed, although bridges and different measures are available to step it down. Unfortunately, those result in poor performance. Some systems have been developed with both a Vesa Local Bus and PCI slots, but because of design compromises, performance often suffered from that. I actually had a Pentium at 100 MHz with an Opti chipset motherboard that had both PCI and Vesa Local Bus. I have paired it with a 2 MB Vesa Local Bus graphic card. I have even used it to play StarCraft on it. What can I tell you, I like living on the edge. Second major problem, speed limitations. The Vesa Local Bus specification provides for speeds up to 66 MHz on the bus, but the electrical characteristics of the Vesa Local Bus connector limit an adapter card to no more than 40 to 50 MHz. In practice, running the Vesa Local Bus at speeds over 33 MHz causes many problems, so 33 MHz has become the acceptable speed limit. Systems that use faster processor buses must buffer and step down the clock on the Vesa Local Bus or add wait states. Our third major problem, electrical limitations. The processor bus has very tight timing rules, guys, which may vary from CPU to CPU. These timing rules were designed for limited loading on the system bus, meaning that the only components originally intended to be connected to it are the external cache and the bus controller chips. As you add more and more cards and circuitry, you increase the electrical load on the system bus, and if it's not implemented correctly, the additional load can lead to problems such as loss of data integrity and timing problems between the CPU and the Vesa Local Bus cards. And guys, those problems eventually summed up. Although the Vesa Local Bus specification provides for as many as 3 cards, there is a general rule: 1 card at 50 MHz, 2 at 40 and 3 at 32 MHz system speed. In practice, these limits cannot usually be reached without problems, so in my opinion, no more than 2 cards per system operating at 32 MHz system bus. Anyway, the only usable cards are VGA and input-output controllers, so actually 2 cards is an acceptable limit. What else can I tell you about the Vesa Local Bus before I move on? The design was very simple indeed. Just take the pins from a 486 processor and run them out to a card connector socket. In other words, the Vesa Local Bus is essentially the raw 486 processor bus. This allowed a very inexpensive design because no additional chipset or interface chips were required. A motherboard designer could add Vesa Local Bus slots to their 486 motherboards very easily and at a very low cost. This is why these slots appeared on virtually all 486 system designs overnight. And although the Vesa Local Bus could be adapted to other processors including the 386 or even Pentium by using bridges and hacks, it was designed for the 486 and worked best as a 486 solution only. Despite the low cost, after a new bus called PCI, that stands for Peripetal Component Interconnect, and I will tell you more about it in my P5 videos. So when PCI appeared, Vesa Local Bus fell into disfavor very quickly. not to mention that Intel pushed for PCI. It never did catch on with Pentium systems, and there was little or no further development of the Vesa Local Bus, which led to the death of it. I have finished reviewing my motherboard, and I will now show you my peripetal controllers. I'm gonna start with this input-output controller here. Nothing fancy, 16-bit low profile ISA. This is the printer port, this is the COM port, another COM port here, floppy disk connector, hard drive connector, and game port to connect the joystick. These two pins here are to connect your front panel LED for disk activity. Those jumpers are here to disable some of the interfaces, and those three chips here are for the RS232 inputs. What else? Many resistors, couple of capacitors, both solid state and electrolytical, and that's about it. I'm gonna put it down and I'm gonna continue with my graphics card. And guys, just look at how enormous and epic my graphics card is. I'm completely in love with it. It is powered by the S3 805 graphical processor, high core Windows accelerator chip, and I'm gonna game the shit out of it when I'm ready. Next to it, this digital to analog converter. You know, on CRTs you need to convert the signal from digital to analog. On later designs and what will become de facto standard, this chip will be integrated into the main processor. Next to it, those 8 chips. This is 1 megabyte of VRAM, but it's expandable to 2 megabytes by those 2 empty slots here. And for my actual build, I'm gonna do that. I'm gonna upgrade it to 2 megabytes and we'll see how it goes. Next to it, this is our video bias and standard VGA connector. Now I'm gonna shut up and just show it to you. I'm gonna put it down gently because it deserves proper treatment, and I'm gonna proceed with my sound card, which is epic as well. And guys, last but not least, from my peripetal cards, my sound card, absolute classics, Creative Sound Blaster 16, and it also has interfaces for hooking up a CD-ROM. I'm gonna hook up a 4-speed Mitsumi to this machine. What else? It has some jumpers. It's not the auto config model, you need to configure this card properly. It has the OPL3 FM synthesizer. It has a creative DSP that has a bug. It's an infamous bug. When you connect a daughter board here, it will distort the sound. This is not great, but I like it with its flaws. This is the stereo amplifier, and this here is the Creative CT1745A mixer chip. This processor is interesting. It's actually an optional extra, not on my card. On my card it's soldered, but I have seen other cards that have socket there and you can bind this additionally. This is a real-time hardware assisted audio compression and decompression, text-to-speech synthesis, and Q-Sound 180-degree virtual audio. Now, what else can I tell you? It's absolutely epic. I have always liked those old creative cards because nothing can compare to the way computers sounded back in the day. I mean, there was no sound and then sound came and it was epic. The only thing I can compare it, and I'm gonna show it to you in my P6 and P5 videos, it's accelerated graphics. Now that completes my peripetals section. I will now show you my drives and I will show you the front of the case I am going to use, after which I will end this video. Guys, you probably remember this drive from last week, Slacky's Core. It's the Western Digital Caviar 2850, 850 megabytes in capacity. It's absolutely perfect for my 486 Vesa Local Bus build. I have no idea what's on it. Let's hope it keeps secrets, and I'll be glad to share those secrets with you in my 486 software episode. I'm gonna leave it carefully, I don't want to damage it. Next to it, this quad speed Mitsumi CD-ROM, perfect drive. very modern for the day. And if you turn it around, you can see me. Hey, yep. I'm gonna hook this up to my Creative, and we're gonna install some software and play some music. Last, again, Mitsumi 3.5-inch 1.44 megabytes in capacity floppy, slightly bigger than the ordinary ones, but I quite like it, and it has a red disc in it. Have no idea what's on. We're gonna figure that out as well. This is the front of the case I am going to use in my 486 build video. It is white in perfect condition and I quite like the design. A couple of things I need to do before that though. I need to fix the turbo button, it needs to be soldered. Then I need to cable manage this chaos here, and I have to configure my front megahertz display. I do not have any documentation, but as I told you before, when you play long enough with those jumpers, there is a pattern, and once you find it, it is easy from that moment on. About my video, guys, I hope you liked it. If you did, give me a thumbs up. If you want to comment something, don't hesitate and do so. I will be glad to reply. And if you like my channel, please subscribe. I need 100 subscribers to change my channel's name. Now next week I'm on a ski vacation, but I will drop an exclusive lucky score video. I have scored 10 graphics card for 20 euros, that's 22 US dollars, and they are all awesome. Thank you for watching, see you soon. Computer Caveman out.